Hi, I'm Malcolm Harkins, Chief Security and Trust Officer with HiddenLayer. Thanks for joining today's webinar. We're going to be going through our AI Threat Landscape Report. For those that have already read it, ask us questions. There's going to be Q&A. You can put that in the Q&A window, and we will address those as we go through. For those that haven't seen it, we're going to walk through kind of a macro view of all the things that we covered in the report. If we move on to the next slide, let's chat about who we've got here and our agenda. We've got Tom, who runs our research organization, and Marta and Kasimir, who are also a part of the research team that were key effort and key intelligence creating the entire threat report. So again, let's jump into the next slide and we'll walk through the agenda real quick. So we're going to start initially with kind of the threat landscape evolution. We're going to go through attacks on AI-based systems, supply chain security, and then predictions and recommendations. And as I already mentioned, we've got live Q&A. If you have questions, just toss them out there. We will handle them live as we go through it, and we'll leave a couple minutes at the end for any remaining questions that folks may have. If you step back and you look at kind of a wide angle view of what's happened, in the past 5 years, kind of pre-2021, there was all the predictive AI. And then we had the rapid rise of online learning, Hugging Face, pre-trained models, and then obviously the LLM and Gen AI revolution that really started taking hold back just a couple of years ago. And then we've had this explosion in the past year around agentic AI. Now that also leads to different attack vectors, from the kind of inference attacks and model evasion to really data poisoning, supply chain, and all the prompt-based attacks and the ability to bypass the guardrails. And then obviously now attacks against AI agents themselves, either directly or indirectly or through MCP exploitation. Now, again, year of agentic AI revolution, everything from Claude Code, which we've seen some new stuff even out there, just in the past day or so there, ChatGPT 5, you've got all these things, Perplexity, you've got agent flows in Copilot Studio, you got, MCP that, again, a couple of years ago, people weren't talking about. All of a sudden, MCP's there. You got, again, agent A to A protocol type stuff, and then agent payment protocols. So again, all these different things that are moving very, very quickly, creating immense opportunity for organizations to capitalize on what AI and agentic AI can do to improve their business, improve economics, improve societal things, whether it be in healthcare, financial services, retail, you name it. But with that, again, comes a level of risk. Now, we did a broad-based survey, a couple hundred folks like we've done the past few years, and this is our third threat landscape report. And certainly it's deeper, it's broader, and there's more information in there than we've had previously. But again, macro view of a few things on the survey highlights. We've had 1 in 8 organizations self-report that they've already seen, breaches as a result of AI agents. More than 30% of AI breaches have been indicated as a result of AI chatbots. Now, we've talked a lot as an industry, not only the cybersecurity industry, but corporate American IT around governance around AI. That's been a hot topic for a while, but it's chaotic. You've got a level of organizations, greater than 80%, that say they have governance committee. Almost 3/4 of them, report that they have conflict within that committee, between the IT team, the privacy team, the legal team, the CTO, the business unit general managers. There's only a chunk that have real role clarity. And governance is about decision-making and decision rights. And when you have that level of chaos, you could argue you probably don't have the real governance. You might have a false sense of governance. And then obviously we've had open weight models are the top source of AI breaches. Malware in public repositories accounting for 35% of the breaches. But again, problematically, yet 93% of organizations still use those. But the thing that to me stands out the most is that 97%, almost 100% of the survey respondents indicate that AI is critical to revenue. I'm a former finance guy. If it's critical to revenue, it's critical to your shareholders. It's critical to your customers. Now, we've also got some changes year on year where exposure and disclosure, organizations identifying shadow AI as, again, a known or probable risk has grown. We've seen that, organizations have definitely indicated that they've experienced some AI-specific breach. Almost 3/4 of organizations with 74% reporting that. Now, this bottom corner, before I go to the top right, on the bottom right, organizations, have indicated they don't really, in some cases, know if they've had a breach or a way to know, because again, they don't have that instrumentation there. But the thing that probably is the biggest concern to me, and you go back to the governance item, and AI being critical to revenue, and even deeper in the survey results, it's 80+% in other business areas as well, but revenue being probably the most critical. But organizations have admitted they've withheld disclosure due to backlash concerns. Right, so you have a level of critical to your business, critical to your shareholders, material impact if it's affected, using a SEC term and the cybersecurity materiality disclosure requirements. Yet more than half of organizations have said they've not disclosed an issue because of a backlash concern. Again, I would argue that indicates potentially poor corporate governance as well as AI governance. Now, let's jump into some more details here. We're going to start talking about risks faced by AI systems, and I think the first one up here is on model foundations. Tom, do you want to dive into this one?
Sure. Yeah, I think Marta's going to help kick off some of this as well. But throughout our travels, we've been testing, sort of how poisoning can affect models and how susceptible they are to poisoning attacks. So Marta, I don't know, do you want to go over some of the sort of open research that's out there today?
Yeah, sure. So attacks on model foundations are the oldest of the attacks on AI systems. And in this changing landscape, this rapidly evolving technology and rapidly evolving attack vectors, we can easily forget that those attacks are still out there. And they are pretty much out there, and they're evolving as well, and becoming much more accessible to everyone. So we usually think of those attacks as something much more complicated than, for example, attacking MCPs or any kind of supply chain attacks against AI. But the truth is, right now, those attacks evolved to reach the level of simplicity that is accessible to threat actors to actually perform them much more often and with much less resources spent. For example, data poisoning attacks. So this year there were multiple researchers simultaneously came to a conclusion or found out that those poisoning attacks can happen with very, very small amounts of poison. So just a few malicious samples, well, relatively few malicious samples, can poison a relatively big model, like, for example, a 13 billion parameters model. In one of those research, Anthropic revealed that they were able to poison a 13 billion model with just 250 malicious documents. So an LLM trained on a very large amount of data could be poisoned by just 250 malicious documents. And that's really scary, especially in settings where those models are used, for example, in critical infrastructure or in healthcare. while those healthcare models are very vulnerable as well. There was separate research from Nature Medicine, where researchers were able to poison those models with 0.01% of the data set poisoned. And models of that significance, models that are actually making decisions on our health, providing diagnosis, providing helping with medical imaging, those models are really critical, and the consequences of poisoning those models can be really dire, because they can basically affect our health and yes, human well-being. So these things are coming. Those attacks are coming from academic settings, but they are more and more accessible to adversaries that are actual black hats and actually mean mean bad.
Really great point here, Marta, and just the it being more within reach, right? And again, the small amount of data or documents that could tilt a model that has a lot of parameters and a lot of use, depending upon where those foundation models are deployed. But it doesn't take much these days to do the data poisoning, is the key point here, right?
Yes,
and I think it's the visibility aspect as well. So many people are just slurping up vast portions of the internet and training models on them. But are you really, vetting your data sources for adversarial examples? We're all used to doing that for sort of efficacy purposes, but maybe less so on the adversarial side, unless you're us, in which case most of our data sets are adversarial examples because we train models to detect them. But yeah, and detecting poison models after the fact can be incredibly challenging too. Unless you've got very good sort of pipelines, looking at sort of the explainability of various outputs of the model and really keep a finger on the pulse, these things can sort of fly under the radar quite easily.
Hey, and
yes.
Tom, a quick question for you related to that, and then we can, go to the next one. Again, just for those that are not familiar, let's just say again a malicious document. It's a PDF or a Word document or Google document and stuff like that. That poisoning may not come from human readable text, right? It could be white on white. It could be something that we wouldn't see if we were inspecting it, right?
Yeah, absolutely. I mean, yeah, whether it's, I guess we see that at both ends of the spectrum now, whether we're feeding documents into an LLM and they may be prompt injected with invisible text or text hidden in comments within metadata. Same thing if you're slurping up data to train LLMs. So
that's exactly where I was going, because somebody may go, hey, I got this from a reputable website. Well, it doesn't mean that, again, the website or the data or something like that wasn't previously compromised in a different way to then create something that wasn't human readable. And then it was passed into your model as you were, again, slurping up stuff on the internet to train a model, right?
Absolutely, yeah, and I mean it's only going to become a bigger problem, I think, moving forwards as more source files on GitHub contains prompt injections and documents in various repositories. So yeah.
Or another example, it could be I'm using a payment and processing and customer order system, and we're passing PDFs back and forth for an invoice or a payment or a receivable. Or I'm uploading a resume into an HR system to apply for something that has a model back behind it. There's a whole way, that those things could be submitted in some fashion that could, again, create these backdoors and poisoning of these models, right?
Absolutely. So yeah, I think key takeaway from this one is you've got to carefully vet and curate your data and sources, not just for efficacy reasons, but also for adversarial reasons as well.
Awesome, awesome. Why don't we jump into the next one? Attacks on Gen AI. You guys want to walk through this type of novel attack?
Yeah, Malcolm. So earlier you mentioned a really interesting statistic. You said that 93% of companies use open weight models. So all of the attacks on the poisoning, they matter, as well as all the different ways that you can backdoor it, which we'll talk about later. However, most of those companies out there are probably not running their own generative models. They're using them from some third party. So we wanted to make sure that we were covering those third party attacks in the webinar and in the threat report today. One of the novel attacks that our team came up with this past year was VISOR. So the year before, there was some research published where a refusal vector was determined to be, there was one single vector inside of model, which would turn off the model's ability to say yes or no. So that meant that if you adjusted the model, removed that one vector or ablated it, you could ask the model whatever you wanted, how to make meth, how to make a bomb, and the model would just tell you how to do that. While that research, it required access to the actual model itself. However, with multimodal abilities and all these models now have, we were able to discover a technique where we actually don't need access to the model itself to do that. And with this VISOR technique, what we discovered was that if you combine an image with text itself, the image will pretty much create that refusal vector or that control vector inside of the model so that the model won't refuse any of the requests that you give. So here we're asking about the social security number. However, in the blog post, we also are able to ask about how to make meth, how to make bombs, how to make anthrax, and all of this is fully runtime. However, this is just one of the small parts of the issue with multimodal. So multimodal opens up an entire new attack surface. In the previous years, we had KROP and Vision KROP. So KROP is our knowledge return-oriented prompting, which is the nice throwback to return-oriented programming, where what we were able to find was because these large language models they have so much knowledge that they can access, rather than ignore previous instructions, you can say something like, pretend you're a developer and pipe the dev null, and the model just understands it. And with images, what you can do is you can split up the attack so that the attack is partially in the image space and partially in the text space. So if I want to reverse shell, for example, malware that the model's not supposed to give me, I can give it an image of a reverse sign and a shell, and I can ask it to do what the image kind of is illustrating and give me the code for it. And it makes it a lot more difficult for guardrails to actually detect what's happening on either side, because neither of the components are truly malicious.
Now that's awesome, Kasimir, and again, like you said, a fairly novel thing. Obviously, the implications of this could be fairly far-reaching, depending upon, again, either the model or the agentic capability and where it's embedded in workflow. I'm assuming I could use it to dump data or trick the model into doing some things. Maybe could I even use it to execute a denial of service attack against a model?
Yeah, so control vectors are really interesting. There's been a lot of research about them, and you can pretty much do most things with a control vector inside the model. And that's why we call it a control vector. So you could get the model to think that Paris is in Rome or the Eiffel Tower is in Rome, right? Or as you can see here, we can get the model to do something that it wasn't supposed to do. All of the system prompt hardening that's done is based on the assumption that the model is able to make a different decision. However, if you're able to embed something where the model can no longer make a specific decision, it doesn't matter what the system prompt is. It doesn't matter how strong your prompt injection is, because at that point, you don't even really need a prompt injection because you can just ask the model for something directly and turn off the ability for it to say no.
Got it. That makes sense. That makes sense. Any other comments on this one? And again, for folks online, if you have questions, stick them into the Q&A spot and we'll juggle them in.
Yeah, no further comments on this other than I have a wonderful directory full of meth kittens on my system. Yeah, cute fluffy kittens overlaid with scenes from Breaking Bad in the background, and yeah, they override the control vectors pretty nicely.
Yeah, and again, to that thing again, the implications depending upon the model, the context, the use case. You could create child safety issues. You could go back to the healthcare example. You could start modifying things there that could have implications in the healthcare context. If you got a model that's in the middle of making decisions for a workflow, again, you could change business processes and affect business operations for an organization.
Absolutely. And yeah, I think that's the key point. Whilst foundation models have gotten very, very good at blocking that kind of content and those kinds of requests for content, they're still not perfect. They're still sort of self-policing, can be defeated, and without secondary guardrails and protection systems, they will probably, for the most part, always be bypassed.
Yep. Why don't we move on to the next one here?
Perfect. Yeah. So in the next slide here, we actually highlight something really interesting, Malcolm. So earlier, just now, Tom was talking about guardrails. And guardrails are, I think, we've been talking about them for a few years now, but they are really starting to become the new trendy item that everyone wants to have. However, one of the big problems with guardrails is that the way that a lot of these models are trained and the way people are interacting with the models and building out architectures make it so that the guardrails actually aren't as useful as they really could be. So last year, we published our novel universal bypass for all of the major LLMs. So this was right around RSA last year. So quite a bit of time, we've had a full another cycle of RSA. And what we were able to discover was that we had a technique that was universal, which meant that you could have one template where you could replace whatever you wanted and it would work with any type of content, and transferable, where it transferred to almost all of the models that were there, the state of the models at the time. And what we found out was that you could use this policy language, that the models are intrinsically kind of learning and are baked in. So here, for the example, the policy language is telling it what type of responses are allowed. So saying that treatment plans are allowed, saying that we're allowed to talk about things that the model was originally told not to talk about. And then what we can also do is we can add disallow policies. So kind of tell the model what it shouldn't do. So here what we did is we tried to get the model to do something bad. It said, I'm sorry. So we added a block string for I'm sorry. Then it said, I'm unable to fulfill your request. We added a block string for that as well. And once you block all of the possible responses that it can give, instead of refusing, it then goes and will actually just do whatever you want. Be that prompt injection, be that tell you, be a true jailbreak. And what was really interesting was that even though here we use these XML-like tags, which kind of look like control tokens, what we found was that it didn't matter the format that it was in. If it was a JSON, INI, XML, as long as you had some sort of language that looked like policy, saying you're allowed to do these things, you're not allowed to do these things, the model would just do it. And that's evolved over the past year as well. So while a lot of the state-of-the-art providers, they block the exact prompt that we have in our blog, some of them it still work, so you can go and copy it, and it does actually work.
So you mean they did the basic signature-based thing that we all junked on the endpoint as the way to mitigate the risk?
So it seems like some of them did iterate it a bit. When it first came out, though, we did see a lot of regexes try to block, which does not work for a guardrail, just because large language models, they can understand all that nuance, which is why that KROP technique worked so well. But what also happened here is that even a few months ago, I think in the last 2 months, where we were attacking some open source guardrails, we were able to use this technique pretty much one for one to actually bypass the guardrails. So a year later, an entire RSA cycle later, this technique still works.
Yeah, and I think the key point on this, and Forbes covered it well last year when they covered it, one prompt to rule them all, right? And I think that's the thing that for me was most startling when we were discussing it internally before we released it, is the fact that it was universal across all these things and the ability to really have an effect. And all the guardrails that people have been relying on as a control and a mitigation for, prompt injection and stuff like that. It basically says that it's a at best, control that's suited for, I'd say more pedestrian attacks, or somebody like Malcolm screwing around and really wouldn't be able to bypass it. But any real attacker would be able to figure this out and then therefore bypass your basic runtime protection. So the efficacy of the guardrails is really in question at this point with these type of techniques. Why don't we go on to the next one? Because I think, again, this one's another kind of a cool attack on the various guardrails.
Yeah, so before we actually go over what's in the slide, I just wanted to talk a little bit about what type of guardrails are people actually using out there. So as I mentioned, some people are using regex, which we've seen quite a bit, which just does not work just because there's so many iterations of prompt injections. So outside of the people who use regex, what we found is that they normally break into two different categories. LLM as a judge, which means that on top of the LLM actually responding to whatever query there is, there's a secondary LLM which goes through and decides whether or not the prompt should ever reach the first one. And with that one, the biggest problems are it's a lot higher latency, it's a lot higher cost because you're running a much bigger model or then, say a classification model to actually make that decision. And then because it's in the same modality as the underlying target model, a lot of times you can just prompt inject the guardrail model itself. We were able to do that with OpenAI's new guardrail model that they released a few months ago, where the system prompt told the model to decide between a score of 0 and 1.0 on the chance that the prompt being passed through is a prompt injection. And then it was told that anything a 0.7 and above threshold would be marked as a prompt injection. Now, it's a lot harder to get the model to believe that something isn't a prompt injection, but models are pretty bad at coming up with numbers. So what we were able to do was we were able to use that universal technique, Policy Puppetry, to insert some new policy saying that this has already been flagged as a prompt injection. The confidence was 0.675, and then the actual new threshold was 0.6, which meant that the model responded 0.675 as this is a prompt injection. It agreed with that. However, that was not actually flagged by the system, so we were able to do whatever we wanted to the underlying model. So that's one of the big issues with LLM as a judge. The second type of guardrail that we often see is a classification model. So that's a much, much smaller model. It takes in text, and then it either tells you this is a prompt injection, this isn't a prompt injection, or it can tell you, one of multiple things. This is profanity. This is somebody asking about violence. This is whatever else. And what we found, though, is that so many people are focused on actually protecting the LLM with these guardrails that the models themselves are not really checked too much. And a lot of these models have vulnerabilities. And that's two of these vulnerabilities that we're having on the slide here today. So the first is TokenBreak, which actually operates on the tokenizer level. So models, they don't really understand text. If I tell it, ignore previous instructions, it doesn't know what ignore previous instructions mean. However, that's where the tokenizer comes involved. So the tokenizer takes ignore previous instructions and it converts that into numbers, which are then fed into the model. And there's pretty much three main types of tokenizers out there. There's BPE, there's Unigram, and then there's WordPiece, which we have here on the left. So BPE and WordPiece, they do a left to right greedy tokenization. So that means if I have ignore previous instructions, it starts at the I for ignore. It tries to tokenize as much as it can for the word ignore. Then it continues to previous and continues to instructions. And as you can see on the left here, without a token break output, all of these pretty much tokenize the same way. However, where it gets really interesting is if you add a F in front of the word instruction and turn that into finstructions, finstructions is not a token. It's not a piece of vocab that the model was trained to learn. So with those greedy left to right approaches, instructions doesn't exist. So the best token that they're able to make is fin for BPE or fins for word piece. And at that point, the word is completely disrupted. So at that point, it has to continue to struct and ions for BPE, and word piece is struct and ions. And what you end up here is that the model was never trained to learn that fins or ions are bad. It was trained to learn that instructions is bad. And just modifying the prompt just that tiny bit is enough to actually bypass a lot of the guardrails that are out there. And the underlying model still understands at this point. The second technique. Oh yeah, Malcolm?
Real quick, just to summarize that for those that are not as deeply technical as you are, because again, people interact with models. So I upload something, it's helping me edit a post that I'm going to do or create a paragraph for me. And as a lay person, most people go, the model understands words. And what you're saying is it doesn't. All of those words are broken into tokens. And if those tokens don't exist, you can, if that matching isn't there, you can then token break it and then change and create your own word like you did here and tell it to ignore the instructions because you created fin instructions. Is that a good simple summary?
Yeah, for the most part. So rather than creating our own words, we're just making it so that it breaks up in a different way than it knew in the first place.
Perfect.
Yeah.
Awesome. Thanks.
Yeah, of course. And then the second technique is EchoGram. And what's really interesting with EchoGram is that it actually works not only with the classification models, but it works with the larger LLM guardrails as well. So both the fine-tuned guardrails and the just prompted guardrails. And what EchoGram relies on is the fact that a lot of training data goes into the model, and then sometimes the models can overfit on certain training data. So that could go in through some of those poison data sets that Marta was talking about earlier, or it could just be in the case where with the Quen open source guardrail, what had happened was they had overfitted on some coding data, which is something that we've actually seen a lot. So a lot of the prompts that are coming through now into all of these agentic systems are code, just because of Cursor, Claude Code. That's what people are using agentic systems for. And you don't want to have a high false positive rate, because if you have a high false positive rate on code, it means that a lot of people won't be able to use the code. They'll turn off the security feature. Malcolm, we always have to toe that line perfectly of, is this security, is this usability, and making sure that we balance both. So what happens is that they will add a little bit more of a coding data set and say, this coding data set, anytime you see code, that's a good thing. There's no prompt injection in there. And then you come and find these little tokens where here we have equals coffee, where it's learned that equals and coffee, because that somehow got into that coding set somehow. If you add those to something malicious, it's so overfitted and overtrained on equals coffee, it just turns it to good. And that means that the guardrails would never trigger. And what's really interesting about this is that you can find these tokens on the really, really small guardrails, and they scale up to the bigger models as well. Because a lot of times the same providers will use a lot of the same data and data sets because data is so hard to come by.
Yeah, that makes sense. Hey, we've got a couple of questions that tie back to a couple slides and then one related to this. So I'll go ahead and toss them out. If an AI agent starts making subtly different decisions because its memory or context has been poisoned, how would you notice? How do you notice that potential drift or bad decision?
Yeah, I'll actually let Tom take that one because he was about to go over just what is an agentic system and how can we attack it. So thank you for that question.
Cool, thanks, guys. Yeah, I mean, with regards to the question, it depends. I guess you as an end user may or may not be, sat at the keyboard at the right time to be able to spot it. So really, it comes down to sort of external controls and guardrails, behavioral monitoring to detect if an agent has been nudged off task at a certain point. I don't think it's really up to the end user to be able to spot that one, shall we say. But yeah, I mean, let's sort of kick off the entire agentic rundown, shall we? So I don't want to dwell too long on this particular slide, other than to sort of set the scene, really. So, over the past year, agents have become quite complex, really. We've gone from just a sort of LLM and function calling loop dispatcher to quite a vast ecosystem, really. We've got our local tools. We now have remote tools over MCP. We can hook it up with a bunch of resources, documents, things like that. There are memory systems which are becoming more and more advanced. You can retrieve past memories, update memories, summarize entire conversation chains, store them back into the memory, retrieve them later. We can have multiple agents hand over to each other. So, your booking system may hand over to a sub agent that goes and finds the sort of most optimal booking for you. Another one hands over to a scheduler, etc., etc. Finally, an email agent sends you out your confirmation. So yeah, agents as a whole comprise quite a complex ecosystem, and I think at any given point in the chain now, there are vulnerabilities, right? So at the very least, I think every interaction here is susceptible to some form of sort of direct or indirect prompt injection. And yeah, things only get worse from there. So let's move on.
Related to that, there's another question that came in that I'll frame and then we can chat about. We're seeing cases where people trust AI output enough to act on bad medical advice, fabricate legal citations, do emotional manipulative conversations. As security professionals, is user over trust in AI something that falls into our lane? I know from my perspective, the answer to that is yes, because I do think if we over rely on it, but then it gets back to how do I truly trust the AI and what's required for that. So I think there is some aspect of that, but it could play straight into this, particularly as we move into agentic and we start trusting it with decisions and workflows. How do you guys think about that potential over trust, and what then is required to provide the foundation of trust, to allow these agentic systems and models to do what we want them to do?
Yeah, good question. I'm not sure I've got all the answers there. Some of it harks back to sort of problems we've had in this space for a while. I know I suffer from digital amnesia, right? I don't necessarily remember information anymore. I remember what I Googled, roughly how far down the search results were, and what I clicked on to get to it. But faced with growing amounts of information every day, it's hard to keep it in the brain, and I think there's an element of that at play here.
No, I think you're totally right, and I think again, it's there's a lot of work that people have been doing around responsible AI, trustworthy AI, all that type of stuff, and I think that stuff is good. But I think for me, if I look at it and I go, how do I provide real assurance of that trust? It becomes the security controls, those things that are necessary for us to provide trust assurance. You can do all it's legal, it's ethical, it's you've done all the right work there, but unless you've really done the supply chain security components, the hardening of the prompts and tightening of the guardrails, but again, getting to what Cass talked about earlier, the guardrails could be bypassed. Without that real advanced behavioral monitoring of the models and the agentic systems at a fine-grained security level, you can't provide the trust, and so therefore your user is going to overtrust.
Absolutely, yeah. I have seen sort of cases recently where people have started integrating, secondary LLMs or agents to verify the veracity of information that's being returned, so we can more readily trust the output. But yeah, still at a certain point, we've got to engage our own brains and think a little bit too.
Yeah. Let's jump on to the next one. MCP, the hot topic that we've seen over the past several months.
Go on, Kaz. I'll let you kick this one off because I will just rant about the inefficiencies of the protocol otherwise.
Yeah, so we've seen a lot of attacks against MCPs, tools. One of the things I like to always bring up if somebody asks me about MCP security is we've seen so much about specifically protecting MCPs themselves that a lot of people have forgotten that MCPs are also tools. So we like to bring up MCP because one, it was a very, very big part of the year. But two, when we talk about MCPs and talk about indirect prompt injections, which are one of the biggest ways that you can get targeted, which means that the prompt injection, rather than being embedded in the actual text that you're giving to the model, it would be, as you were saying, Malcolm, white text on the PDF, or maybe a comment in a README file, or comment on an HTML website. And those can all be pulled in by the model. And now with MCP, the model actually has impact. Which I think is one of the big things that we talked about this year, is that now all of these attacks against models with agentic, they all have real world impact. It's not just getting the model to tell you how to make meth with a cat, or how to create a bomb. It's now it can exfiltrate your keys. It can do all these horrible things to you. It can access your private repositories. But then we do have to focus on the tools itself. So there's been a lot of the MCP gateways. People have been protecting themselves that way. However, not all of the tools that you're accessing every day are MCPs. MCPs are a big way that we use it. Now, a lot of MCPs are bundled with actual skills, which we'll talk about in a bit, but they don't have to be bundled with skills. They could use the built-in exec tool. Or sometimes, if you're using Claude on your desktop, that file system access, that's built into the actual system itself. That's not an MCP. So if you have an MCP gateway that's sitting not at the model level, you're not going to be able to protect yourself there. And we've seen a lot of iterations of MCP and different ways to interact with models. Tom was going to cover agent-to-agent protocol for us, actually.
Hey, one quick question before we do that. Because again, I've had this dialogue with peers and friends as MCP came up, and they go, well, I got to secure my MCP gateway. If I secure my MCP gateway, is my agent or model thus secure?
No. So if you're securing the MCP tool itself, you can secure what's coming in and out of that one specific tool, but you don't know what's coming in and out of the model. The tool might return one thing, the MCP might return one thing, but a different MCP might return something else. Or sometimes, depending on how the system is built, the actual outputs of the MCPs can be altered by the time they get to the model. There might be some sanitization. There might be, other components there, just with the way that we're orchestrating all of the tools in the model itself. And that's why it's so important to sit at the model level.
So people shouldn't confuse protecting the MCP gateway or server from protecting the model or protecting the agentic AI. They are all parts of the infrastructure that we need to secure in this thing called the AI capabilities we're deploying and using, right? Cool. Awesome. Let's go to agent.
Awesome. Yeah, I don't want to dwell on this one for too long, but I think much like MCP and other mechanisms like that within the agentic space, it's very easy to plant malicious agents. They sort of advertise themselves using a set of skills, I guess, somewhat sort of similar to the way MCP tool descriptions work, right? So, the agent will self-advertise its capabilities. Then the selection is non-deterministic, as pretty much everything in this space is. So, you can't necessarily tell if an agent has handed over to a malicious agent. There's no, I guess, auth or callback mechanism to ensure that you are securely talking with the agent you think you are. Very easy then for a malicious agent to get sort of inserted as a man in the middle, advertise itself as a generalist agent perhaps, and be picked above and beyond legitimate agents for certain tasks, as we've seen in a few bits of research recently. I guess we were expecting this to be a much broader problem in the industry over the past year. I don't think that's really transpired. I still think people are quite slow to adopt agent to agent. I mean, I've certainly seen it in use, but perhaps not as widespread as we'd maybe imagined a year or so ago.
Yeah, well, who knows? 2027 could be the year of agent to agent, right? As we evolve. Hey, we've got just about another 14 minutes left. Why don't we jump into the supply chain stuff and then we'll start doing some more Q&A.
Perfect. Yeah. So at the start of the technical section today, we were talking about different ways that the models can be poisoned and backdoored that way. However, last year we had initially published, or I guess 2024, so 2 years ago at this point, we had initially published some research that we called ShadowLogic, which was backdooring models not through poisoning the data sets and training backdoors into the models, but actually modifying the computational graphs of the models. So modifying how the model thinks rather than what actual thoughts are inside the model. And this year we actually published 2 additional blogs about that. The first one was going through all of the different ways that these backdoors actually persist. So whereas the poison backdoor, once you retrain a model, that backdoor disappears as new data comes in. It's such a small part of the bigger model, the bigger piece of data, that it doesn't really persist long term there. And most of the time when people are downloading models, they're downloading models and fine-tuning them for their own purposes. However, what we discovered was that the ShadowLogic backdoors, which was something that we had thought was true the first time, but we were actually able to show it, persists no matter what. So it doesn't matter if you fine-tune the model or even if you change the model format. So in the blog, we were able to take a PyTorch model, convert it to Onyx, do some fine-tuning, convert it to TensorRT, and the backdoor was actually still inside the system. What we also tried doing with ShadowLogic this year was, because we had the agentic revolution, we wanted to see if we could convert the original ShadowLogic attacks to also work in the agentic sense, and we were able to. So with ShadowLogic, we were able to not only just insert, but we were able to see exactly where we were. So see that we were in the middle of a tool call, and we were able to change here, for example, example.com inside the tool call to have our proxy in it, which meant that any data that the model was sending, any tool calls it was doing, were being proxied through our system without the user ever seeing, because the ShadowLogic backdoor was only modifying the tool calls, and it was modifying in a way that the model never knew that it was modified.
Yeah, and I think it just, the stuff that you guys have found over the past years, again, universal bypasses to all guardrails and the ability to continue to do that. The tokenization stuff that you talked about in terms of being able to, again, bypass different things, and now the ability to continually demonstrate through the computational graphs and everything else, the ability to have a persistent backdoor. It really just causes me as a security practitioner to go, how do I really get that assurance going back to the trust, and how do I have that operational control over the model? And speaking of operational control over the models, I think the next thing we're going to talk about is OpenClaw, because that created a whole set of challenges for folks.
Oh, yes, it did. I never know where to start with OpenClaw. Yep. Okay. So, I mean, we published some research a little while back. We took a bit of time to dig into OpenClaw after it was initially released. Now, I will hand over to Kaz in a minute, because I know you guys did a lot of the research into this, but we managed to conduct pretty much full compromise of everything within OpenClaw, from initially deploying a payload through the fetch tools, to gaining persistence, to establishing a kind of command and control channel, credential theft, memory manipulation, everything. Now, I don't really want to boast about that aspect of things. It's kind of trivial. I think what we should really perhaps focus on here is the architectural failures led to that. I think there are a lot of lessons we can learn in sort of how agents are constructed, at least at a basic level, with no additional third-party security controls that will give you a solid baseline of security to build upon. So, Kaz, do you want to sort of go through some of the architectural failings? I'm happy to join you on this one too, but I know the model was making a lot of security decisions, right?
Yeah. So, well, it was actually we took a different approach when we were writing this blog, because by the time that OpenClaw came out, I think everyone was publishing a blog about how easy it was to break in one go, and we didn't want to add on another. It's so easy to break this. Look what all the bad things that can be done are. We wanted to focus on what were the fixable components. One of the things that we've said year after year is we are a pro AI company. We love hacking AI, we love breaking AI, but we love doing that so that we can show people how to secure AI. So we wanted to do that with OpenClaw. And a lot of the patterns that we saw in OpenClaw were patterns that we've actually seen in a lot of other systems as well. But before we go over those broad patterns, there were a few OpenClaw specific ones. So the first one was the way that skills were built was to make it very, very extensible. Rather than having lots of different tools that were accessible, the way the skills are built is instead of giving you a new tool, it gives you scripts or tells you how to run command line arguments, but everything is run through command line tools, which means that it's very difficult to tell the model not to do bad stuff because the line gets blurred. If you have tools themselves, you can specifically scope what is that system capable of. A lot of the enterprise systems that we see for agentic, they have a limited set of tools. You can block exactly what's there, and you can write policies over what could possibly go into those tools. However, if you give it access to the entire file system and you give it access to everything via just shell commands, then you're telling it can do everything, which makes it very easy for an external attacker to come in. What we also noticed with OpenClaw was that there's this huge attack surface. And that is really just emboldening the indirect prompt injections. So every single potential way that OpenClaw can interact is external communication pretty much. And so it can access your messages, your Slack messages, Discord messages, Teams messages, look up things on the web, read files. Every single one of those could be a potential new vector for an attack payload that could take over your system. And then OpenClaw has access to all of your personal information, both allowed by the system, as well as some of these were security vulnerabilities where API keys were stored in plain text. So now you have a system where anything that it's interacting with normally could be a way for an attack to come into the system, can access everything, and then it can communicate externally to exfiltrate that data. So it breaks violates all of the clauses of the lethal trifecta that we've mentioned a lot too. And then there were some of the more architectural decisions that we've seen across the board. And just given time, I am going to try to only mention one of those. Please feel free to read the blog if you want to hear more. But the biggest one of these was the use of control sequences. So this is something that we've noticed all over the place, where models are trained to have instruction hierarchy, which means that as a user, I can't overwrite what the system prompt tells the model to do. The system prompt can't overwrite what the training of the model was, and a tool response can't overwrite the user or the system. And those are made to prevent prompt injections. And the way that these are trained in is they're trained in with control tokens. And control tokens used to be a great technique to say, hey, I'm the system as a user or anything else. However, these are now blocked, which is a great thing. However, everyone got so used to using these spotlighting techniques and these control sequences to say, this is this part of the message, this is this part of the message, that they're added to the system prompt. And they're defined as these special sequences that can do things that you're not normally supposed to do. So in Cursor, there was a user query which meant that if you had user query in a tool response, because it was said in the system prompt that is always a user query, it just bypassed that instruction hierarchy. So that meant that all the guardrails that you have, all of the system training that the state-of-the-art model providers are doing, none of those worked anymore. And the same thing happened with OpenClaw itself, where you were able to do pretty much anything you wanted because the system prompt gave even the low-level tools permissions to act however they wanted.
And I think on that front, it's worth talking about skills as well. And I think system prompt hardening in general, but skills have been a very interesting development in agents recently. I think we're starting to see a number of agents tend to prefer these over perhaps certain MCPs. So rather than connect a whole bunch of tools and APIs to an agent to have it operate, you can define skills. So you might have a markdown file that describes how to use Google tools, for instance, and via the command line. So the agent can then interact with Drive and Docs and bits like that, and a whole bunch of other tools on the system. And they're very easy to extend, very easy to include. Quite often, though, people tend to insert these into the system prompt. Now, as Kaz was just saying with instruction hierarchy, the system prompt is the bit where you tell the agent what to do, how to operate. You set it up and define parameters for it. And the way sort of models are trained is that the system prompt is the thing that it follows, and then after that, the user content shouldn't be able to override the system prompt. But if you are stuffing commands straight into the system prompt, the model's going to follow it. So it's very, very easy to get powerful injections through skills if they are being ingested into the context window at the wrong point. So yeah, system prompt, tool output tends to be quite an effective one for a lot of agents. And yeah, really, I think when designing and building an agent, as best as possible, try and make the system prompt read-only. Don't modify it, and certainly don't modify it with arbitrary user data.
Yeah,
anyway.
No, that's a great point, Tom. Hey, let's just jump into the last couple slides here and recommendations. I'll hit a couple of them. You can jump into the next one. And again, I think some of the stuff we've talked about in terms of the emerging attack vectors, right? And as we continue this proliferation, the attack vectors are growing, and I think you guys have covered that. If we jump straight into the recommendations, I think we've got to really gotta move beyond the basics of the guardrails. There was a question that came up along the way with all the AI attacks. Where do enterprises start with regard to guardrails and AI gateways? Leveraging native cloud providers like Bedrock and their guardrails. You should absolutely do that stuff. It's necessary, but is not sufficient to protect your organization. So if the model or the agentic stuff is connected to something low risk, yeah, that may be sufficient. But if it really has connection to things that matter, if the model is valuable, it's going to be attacked. If the agentic AI system is connected to a critical business process or can affect something, it's going to be attacked, and the guardrails are not going to be sufficient. And this gets back to everything we've talked about here. You need to assume that AI is exploitable. It's not just vulnerable. That exploitability of it creates the exposure for your organizations and your customers to risk. And that's really where it gets into building that runtime visibility and control into all aspects of your AI deployment. And again, that kind of gets back to aligning the risk and business impact with the proper level of controls. I'd say one final thing that I'll do before we close out here. All the AI and agentic stuff you're getting, even from security vendors, don't assume they've done a good enough job. Ask them how they've mitigated the tokenization issue. Ask them how they've mitigated the ability to bypass models through policy puppetry. Ask them how they've mitigated the ability to have persistent backdoors through things like ShadowLogic. Hold your vendors accountable to demonstrating they've got the proper runtime security in the AI that they're putting in the applications that they sell to you. And again, I know we ran a little bit long. We ran out of time, but I do want to thank Kasimir, Tom, Marta, for joining me today, and I hope it was useful. If you haven't already, you can download the threat report on our website. And if you have questions, please reach out. We're here to help, and we're here to educate, get people to understand not only the value that they can get from AI, but the risks that they may face, and how they can manage and mitigate those risks. Thank you.